Okay, looks like we can get started. My name is Nancy. I'm one of the volunteers here at the museum. So thank you for joining us this afternoon. And another of the volunteers that we have in the room, besides you and you, is Dr. Terry Panhorst, who's been a volunteer with the museum for years and years and has done a number of community outreach programs, was on the board for many years, and spends his summertime explaining to at least 500 children how those crystals got into the geodes. And
that's in 1 hour.
So Terry has his PhD from the University of Nevada and is a retired professor at the University of Mississippi in the geologic sciences.
Yes.
And so Terry, regarding geodes, is that a critical mineral? I mean, it's important in my rock collection.
Geodes?
Does it meet the standards for critical minerals?
No. Rest assured.
Okay. So, everybody, Terry Panhorst.
Okay, we got a couple people still wandering in, so we'll let them grab a seat. Well, first of all, thank you all for showing up on this somewhat blustery fall day, but I appreciate the turnout. And I got to give credit to this talk, actually, or at least the idea for this talk, to Shirley, because much earlier this year, yeah, right, you suggested that maybe that would be a good thing to talk about, and so I started. That's how I also spent part of my summer, was assembling information and going through stuff to be able to present this topic to you all this fall at some point. And the news media has been working with me, because almost on a daily basis there's more information, new restrictions are posted or something like that. So it's these topics of critical minerals, and which includes the rare earth elements, is rather timely, I think, because we just are bombarded with it in the news just almost constantly. However, reading a number of these articles, I can recognize that in many cases, the people writing the articles, or the people that they're interviewing for the articles, have a very limited understanding of what critical minerals really are and what rare earths are. They know a few bits and bytes here, but by and large, I think there's a gap in their background. And that's my goal today, is to sort of fill in some of the background for y'all so that you have a better appreciation of this stuff. This topic is very complex. That's the first thing I'll say. And it's not going to get any simpler over time, because there's a lot of important decisions that have to be made regarding these things. So, just as a sort of an outline of what we're talking about today, and since this is going to be a little bit of a lengthy sort of presentation, there is a break scheduled about halfway through, which is a prime opportunity. Anybody needs to run out screaming and hop in your car, it won't hurt my feelings. You know, it'll be okay. I'm used to students doing that all the time, so no problem. But first, we're going to have just a little bit of background information on things that I'm going to be using through the talk for illustration purposes. And I want to make sure we're all sort of on the same page with that. Secondly, then we're going to go into the importance of these so-called non-fuel mineral commodities. You're going to be seeing that a lot today, that phrase, non-fuel mineral commodities. So by non-fuel, that means it doesn't include oil and gas, doesn't include uranium, doesn't include coal. So what we're talking about here are the other mineral commodities that we use. But their importance to the U.S. economy. All right? We'll follow that up with a bit of a more in-depth look at critical minerals. In other words, what are critical minerals and how do we define them in particular? How are they determined? It's not just something that's randomly done by any means. And then we will probably take a break somewhere about that point, and then come back and discuss in a little bit, quite a bit more detail about rare earth elements. Okay, so that's the plan for today. So in terms of the background that we're going to start with, okay, I've got a handout here of a diagram that's kind of important to you, and Nancy, who is right here, hold on to that for just a second, okay? Because what we're going to start with is something that probably will send shudders through you, if you have everybody but Coyote anyway, if you have any recollection of the periodic table of elements.
Yes.
All right, and she walks around. Yeah, she's got a. Very good. Okay. Well, good. I have a cell phone. You've got that. That's great, though. Now, realize this diagram, like most of the diagrams, includes all of the naturally occurring elements and all the man-made elements that we've created. All right. Well, that's not exactly useful to us because there are no man-made elements that are used in industry. So all we're going to focus on today are the 92 naturally occurring elements in the Earth's crust, because that's what industry uses. And that's the diagram I have for you. Nancy, if you want to go ahead and just start passing that out. Now, the reason I've included this is not that I expect you to memorize it or read it or anything like that. It's a very handy way to illustrate a whole bunch of information in one concise little diagram that you can grasp fairly easily. And exactly all the little details, I'll leave that up to you. You can search that out later on your own time. But this is merely a way to show some quick illustrations of things. And to do that, let me show you, I'm going to show you an example of what I'm talking about. That's very much applies to the topic we're talking about today. And that involves these guys. Good old computer chips. Everybody, almost everybody in this room probably has at least one computer chip right now in your pocket. And it's in your cell phone. If you drove here in a car, it's got a bunch of computer chips in it. Your house has a bunch of computer chips in it. In your refrigerator, all right? Maybe in your washing machine. Various things like that are smart machines. All right, well, they're smart because they have computer chips in them. All right. Well, if you look at the history of computer chips, you see a very interesting trend in terms of the elements that were used. So let's go back in time a little bit, way back to the dark ages on computer terms of the 1980s. All right. During the 1980s, there were 12 elements illustrated by this light blue pattern on this diagram that were used in the construction of computer chips. And if you recall using a computer, if you used a computer in the 1980s, I mean, they were at the time, they were really functional, and that was great stuff. Nowadays, those things are, of course, dinosaurs, because they, relatively speaking, work so slow. And all the chips were, well, the suckers were big. You could actually see them. You know? Well, go forward 10 years. Go into the 1990s. Now, computer chips are made with 16 elements. So we've added 4 by this point. The ones that are marked in the green. So several of them. Things like titanium and bromine and other things. I don't know exactly what they do in the computer chip, and that's not what the focus of the talk is today. But the point is, by the 1990s, we were up to 16 elements. Obviously, improvements. Go forward again, come closer to nowadays, another decade. And in the early 2000s, this thing balloons to 61 elements that are now used in computer chips. And these are the ones that are shown by that sort of orangish tan color. So we're using a whole bunch more of them. These computer chips, they're getting faster because of that. They're getting much smaller, tiny little things, incredibly small now, because of the enhancements that can be built into these chips with these new elements that we're using. Now, that wasn't so hard, was it? Okay, that's what I'm going to be using this diagram for, to illustrate things as we go through. Okay, because what we're going to do now is jump immediately. First of all, are there any questions about that?
Well, that's one of the things that I was going to say. Have you been told about the use of doping agents in the new computers that makes the chips very, very faster?
Yeah.
The doping agents is what they're talking about, those green elements and the brown elements especially.
Yeah, yeah. It's the use of those elements that allow us just amazing enhancements in those chips, which apparently is just going to continue as long as people are working on these things. Okay. Next thing I want to talk about is the importance of these non-fuel mineral commodities. And I've got another diagram, which I'm going to give you a copy because there's some small print on here that might be a little hard to read. Certainly you can't read it on the screen. Even here, it might be a challenge. But we'll get started with that. The diagram looks like this. Now, the one I'm giving you is not in color. But if you go to the USGS website, you can get this diagram in all that luscious color right there. Yeah, you can go ahead and pass those out. So what this is a model, an explanation, a diagram that the U.S. Geological Survey publishes every year. They update it every year, that shows the importance of mineral commodities to the U.S. overall economy. And to go through this diagram, I think the best way to do it is actually not from left to right. What we're going to do is go through it right to left. In other words, we're going to start with this block right here on the right, the one I've outlined in red. Okay, that block represents the total U.S. economy represented by the gross domestic product, the GDP, which we hear a lot in the news. That's basically the sum of all the goods and services that the U.S. economy produces. And we use the GDP as a comparison with other countries to determine economic progress, economic wealth, things like that. So it's a useful diagram that way. Okay. Essentially $29 trillion, an enormous number. It's kind of hard to wrap your head around. But keep in mind, it's maybe just 29, okay? 29 trillion dollars. No, 29 trillion. Yeah, it's 29,000 million. Okay, so, or excuse me, billion. So it's $29 trillion. Enormous numbers. Okay, so that's the U.S. economy. Now, if we back up one box, back to here, this is, as it describes, this is the value added to the GDP by major industries that consume these processed mineral materials. So these are the producers which are selling things which go into here. That these these industries directly consume mineral products. All right, and that value there is $4 trillion. So basically, of this $29 trillion, 4 trillion of that, or one could think of it as 14% of the GDP, is accounted for by industries that use these mineral products in construction. Think of things like automobiles, Okay, that uses a lot of materials. All right, so that's a sizable number. I mean, politicians look at the GDP, and if it goes up or down 1 or 2%, they start getting either really excited or really nervous. So, small swings in the GDP have a lot of impact. So 14%, obviously, that's a fairly sizable impact there. Okay, move one to the left. This column right here. These are the domestically processed, okay, mineral materials. Things like aluminum, as they list there, aluminum, brick, cement. These are the ones that are domestically. So in other words, the ones that the US create. Now, going into that also is this box down here, which is the imports of those types of materials. We import metals. There's various materials that we import and use. We also export a bunch of stuff. And so what they do is they take the net, they take the imports and then you subtract the exports, you come up with a net value. That's why it says net. Account for it that way. Well, that's 77 billion, and that combines with this 900 billion over there. So you're looking at almost $1 trillion. Yeah.
You know some of the key import-export raw materials like that?
Well, as they list here, like metals, various chemicals. And we're going to be talking about some of the key ones because a lot of those are going to be what we're going to define as critical minerals, right? So almost $1 trillion is represented here, which feeds into these major industries, which then feeds into the gross domestic product. All right. Now, down here, they give a disclaimer that says you can't directly compare this to that because it goes through this intermediate step. Well, I'm going to violate that. All right. I'm going to throw that rule out the window and say, yeah, I'm going to compare it directly. So there you're looking at 3% of the GDP actually feeds into this number here. That's reasonable. I'm trying to give you a sense of the importance of this. Okay, if we move to the left over here, now we're looking at domestically mined raw minerals. That's things when you talk about mining, that's what we think about. The big trucks running in and out of the hole loaded with materials, and things are processing. Okay, that is the domestically mined raw materials. Copper ores, iron ore, sand and gravel, stone, all that kind of stuff that we consume all the time. That feeds into here. Part of what this is, however, that domestic stuff is exported. Other people buy it from us. Okay, so we really need to include both of these in here because the stuff that goes into this box, well, along the way, part of it gets diverted into exports. And then we import some other stuff that would normally be involved with that. And so again, they're looking at a net value, just to keep the numbers straight. Economists design these things many times, so you have to, kind of let them do their thing. Now down here, we've got a couple boxes that I'll just really briefly talk about, and that involves the recycled stuff. We do recycle materials in this country, and so you have a certain amount of domestically recycled metals. All right, well, those can be fed back into this stream up here, which goes into the domestically processed minerals. All right, now you'll see this number down here, value of old scrap. Does anybody know what old scrap is?
Yeah. Ancient computer chip motherboards and things.
Not necessarily. It's broader than that.
Well, we have a lot of aluminum and stuff in cars. I don't know if it's...
Okay, old scrap is material that has gone through the consumer. Recycling centers, that's all considered old scrap because it's gone through the consumer. Okay. Now, there's new scrap. New scrap is stuff that never left the factory. You know, you got some guy working some sort of aluminum. He's doing some finishing on aluminum, and you get aluminum scrapings that fall onto the floor. They sweep those up, and what do? They're not going to throw them out. You can use those, put those back in the bin, and they can get reprocessed. So that's new scrap because it never really left the factory. Old scrap is stuff that has left the factory and gone on. We also export a certain amount of that. And so that's what's accounted for by that box down here. By the way, what is the most recycled metal in the United States? No. Most people think it's aluminum, right? They think aluminum cans. Yeah. Nope.
Steel.
No. Really? Lead. Because everyone who has a car has a car battery.
Oh, yeah.
And what do you do with a car battery if you need a new battery? You turn it in. What happens to that lead? They reprocess it and reuse it. So recycling on lead is up over 90%. All right. Aluminum is actually down around 30 or 40%. And part of that is because a lot of it goes to the landfill. A lot of it gets put into something that can't be recycled for a long period of time. You know, a lot of aluminum goes into aircraft. Well, you're not throwing away an aircraft after a year. Obviously, they'll stay in service for decades. All right, so it's not to a place where it can be recycled. Yeah.
I heard something interesting in that the kind of stats you're talking about in terms of recycling differ by country.
Oh, yeah.
And I mean, I've heard, for example, in Europe, literally 90% of all aluminum gets recycled, whereas we're much lower.
Well, and I'm sure there's various reasons for that, which we won't get into. Okay, now let's move on to the final handout I've got here that you can refer to this again as we go through the rest of the talk. And this is another diagram that USGS puts out on an annual basis. This one, since it's hard to read, not only obviously you can't read it on the screen, you might be able to read it on the handout, but I've got an enlargement of it on an easel back here. So during the break or afterwards, you can go up and take a look at it. If you wish, you can take a photo of it and use it that way. What we've got here is, let me just move ahead here so you can see the top of the thing. It is for 2024, because that's the last year that we've got full data on. All right. It's the U.S. net import reliance. Okay, reliance. So that means how much do we rely on imports to meet our needs for this particular commodity? That's all it's listing here. So there's various columns on here.
Which it could be a very small amount. So, for instance, arsenic, it could be a very small amount of arsenic in total.
Right, right. All this is of all the arsenic we use, what percent do we import? Yeah, that's how it's categorized. That's how it's tracked by the USGS. Okay, this first column over here has all the mineral commodities on it. Now, the first thing I'll say is that not all the mineral commodities are on this diagram you're holding in your hand. They cut it off at 20%, which means if we import 20% or less to meet our needs, it's not included in this diagram. All right, and that's part of it's a space-saving thing, and part of it is that those are much less likely to be ever considered critical. I mean, if we're already producing 80% of what we need, the chances of that being critical listed as a critical mineral is pretty low, I would say. Okay, so that's the list of minerals over here. This center column is the net import reliance as a percentage of the apparent consumption. And the USGS always says apparent consumption because they're always having to make estimates on what the actual consumption is for any particular commodity. It's a very educated guess, but nonetheless it is still a guess, an estimation of it. Now this is done two ways. The big colored one on the screen here is a visual representation of percentage, so from 0 to 100%. And then the number next to it on the left side here is just the actual number that they're representing. And I will say that whenever they have numbers that are the same, for instance, if you look at this top group here, all of these are at 100. All right, then what they'll do is they will list the mineral commodities in alphabetical order. So there's nothing fundamentally important about the order of the listing on here when all the numbers are the same. They just do it in alphabetical order just for ease of finding information on the diagram if you're trying to, look at it. All right, then thirdly, this list is the leading import source. In other words, what country are we getting this material from? Now, to do this, they don't look at just 1 year. They actually took the average from 2020 to 2023. So there's 4 years worth of data that they're looking at. And they're saying, okay, over those 4 years, what country did we get the most from? Which country did we get the second most from? And rank it that way. And when they list it, they only listed the top 4 countries at the most. If there's less than 4 listed, then that means, okay, that's a complete list. But if there's 4 or more, that means, well, it might be 4 countries, it might be 14 countries. Okay, so they just take the top ones there, just to kind of give an idea of it. Okay, everybody sort of get an idea of this diagram? Okay, now, the reason I'm showing this is that there's some important things you can do with this. You can see on this diagram right here, if you start looking at stuff. So what I'm going to do is I'm going to zoom in toward the top half of this, if you want to follow along. And I'm going to look at 3 commodities in particular. 3 commodities, okay? Manganese. We import 100% of manganese that we get. All right? The second commodity I was going to look at is titanium. Good stuff, titanium. We import 86% titanium to meet our needs. And the third thing is down here, chromium. We import 77%. So clearly, those 3 we import a lot from. And those 3 metals are critically important to the aerospace industry, to the airline industry, any industry that uses steel, particularly steel that has to be enhanced for various purposes. Particularly strong or resistant steels, like the chemical industry needs special steels because it's pumping around a lot of nasty things in tanks. And those have to be lined with particular things. Now, if you look at the import sources for those 3, just those 3 commodities right there, you'll note that South Africa is either the most important or the second most important source of those 3 metals in particular. So I would argue it's no wonder that the United States is interested in the political stability of South Africa.
No kidding.
to avoid any sort of interruption of those materials being exported to this country. Because if all of a sudden we lost that, that could be rather serious to a number of industries. So very quickly in this, when you start getting into this, you start seeing some of the things that might be considered criteria for designating critical minerals. Okay? How much do we import? Where do we import from? All right? And what's the political situation or the stability, as the USGS expresses it, the risk of supply interruption?
Oh, yeah.
Yeah, which are not easy questions to answer. Okay, now another way to view some of this information, which the USGS has done, and I'm thankful that they've done this, is they've looked at the materials which we import that we are greater than 50% reliant on imports, which basically defines this box right here. Everything from tungsten all the way up. And if you look at the sources of imports that we get, all those countries, there's a whole bunch of them in there, but there's an awful lot of repeats. Well, there's an easier way to look at this. Look at it in a map view. And I know you can't really see closely on the map, but one of the things you can see, we sit here, the ranking is, as you get closer to red, that means the more important that country is as a source of imports to us. Okay? There's obvious two big players here in terms of imports. Canada, very close to us, and China, a lot further away. Those are the two biggest sources. Well, that also brings up, okay, what are our relations with Canada like compared to our relations with China? All right, big difference, big difference. All right, so that's something else that has to get weighed into these sorts of considerations. Second most important are going to be like countries like Mexico and Brazil, and I mentioned South Africa, which sends us a lot of metals. And then it goes down from there. Ones that are in white, we don't actually import any mineral commodities from them. But we get it from quite a bit of places all over the world. Okay, yeah.
Terry, how are those minerals shipped to the U.S.?
The shipping of the minerals mostly, if they're in bulk form, is done by ocean. You know, they do that transport just because it is so cheap. It's the cheapest way to do it, and you can bring in large masses of it. I mean, that's basically, it's very similar to what we do with oil. If we're importing oil, it's sent through these tankers. People are familiar with that. Well, we've also got large shipping vessels carrying containers full of mineral commodities, doing the same thing. Yeah. Yeah.
Is that little orange just Germany, or is it Germany, Belgium?
Oh, no, actually, that's Germany. And yeah, that's because they actually, they process a lot of things in Germany, and then we import that to work with those materials and then use it in our own materials. Okay. Now, that's going to lead me into critical minerals. Okay, so we need to really start talking. We've already been talking about critical minerals, let's face it. Okay, but now we need to start focusing exactly on critical minerals. And so what we're going to do is we're going to start with asking the question, okay, what should be considered? What do we need to consider when we are defining a critical mineral? Okay, well, we've already talked about a bunch of that stuff. All right, how is the commodity used? In other words, in what industry is it used? All right, Defense industry, that's pretty important to national security. The playground industry, a little less important.
Yeah, so.
They both use metals, but in different ways, obviously. So how it's used, what industry it's used in, obviously, should have some sort of influence, some sort of ranking in there. Okay? How much of what we consume is imported? Well, we already kind of addressed that. That's actually a lot simpler thing to evaluate because the USGS has been doing that for years on that diagram that we've got the enlargement of back there, and you've got a copy in your hand. So that we have some experience at. Yeah.
Have all those calculations been made assuming there is no suitable substitute?
No. Oftentimes you can find suitable substitutes. Now, the issue gets into how do you define suitable?
Right.
Generally, if it's a substitute, it means that the finished material is going to cost more because it's more expensive to use the substitute, or there's going to be a diminishing in the results, the quality of whatever the finished thing is.
It may not do the job as well.
May not do the job as well. That computer chip may not be quite as fast if they have to substitute something. So you can't ignore that, but how much influence are you going to give that? Those are the kind of issues you have to deal with in here. Okay, obviously where the imports are coming from, another important question that should be in some fashion considered in here. All right, what is the impact of a potential shortage on the U.S. economy? Okay, how is that going to affect us? Hard things to evaluate, but necessary things. Okay, is there what's called a single point of failure? Which is like, whoa, what does that mean? Let me give you an example. A really good example is the element beryllium. Okay, beryllium's a real light metal. We don't use a whole lot of beryllium. It's used in some telecommunications, various things like that. So it's got this little niche here and there. We are actually a net exporter of beryllium. We mine and process more beryllium than we use. And so we're actually exporting it to the world. What sounds like, whoa, but we're set then, right?
Not exactly.
No, we're not set because beryllium is a really good example of a single point of failure. Why? It's only mined one place. Spore Mountain, Utah is the sole source of beryllium in this country. The company takes that, it ships it someplace else where it gets processed into the beryllium that's then sold to industry, and then they use it. So that's considered a single point of failure, and therefore, if something, God forbid, if something were to happen to that mine, major earthquake, shuts the thing down for 6 months while they go in and repair stuff. All right? That could pose a threat to the economy. So they also have to, the USGS, when I'm saying they have to evaluate that aspect of it. And this is something that's kind of actually relatively new in their evaluation process. They're really trying to consider and incorporate that. So there are a few elements in there that on other appearances would be, well, this seems pretty stable. I mean, why would this, why would I be worried about this mineral commodity? Well, it's because it suffers from this single point of failure scenario. And so we have to be alert to that. And then finally, a topic that's already come up, suitable substitutes. Are they available? What do they cost? How well do they do the job? Those types of things. So, we've talked about a number of these things. All right. And we can sort of give you a feel for stuff in a very qualitative sense. What the USGS has been doing in their reviews of this is they've been going through and actually doing a very quantified assessment. They have been applying things like probabilities to scenarios that, well, if this were to happen, what would be the downstream effect of that to the economy? And actually throwing numbers, getting numbers onto that.
Domino effect might really blow it.
Well, okay, so to sort of give you guys an idea of what I'm talking about here, we're going to introduce what's called a mineral criticality diagram. How critical a mineral might be. And so I'm going to build a very simplified diagram here on the screen, walk through it. It's very qualitative, so there's not numbers on it or anything. It's just like, well, low, medium, high kind of thing. You know, just to give you an idea. Okay, so first we're going to start with a box. Every good diagram needs to start with a box. All right, doesn't matter exactly what shape the box is or color, but you got to start with a box, right? Because that defines a couple of really nice axes for us. Down here along the bottom, we're going to talk about the supply risk. In other words, what is the potential for some sort of disruption? Is it a single point of failure? What's the political stability? Other things like that, all those aspects. What is the potential for some form of a disruption in the supply? And as mentioned, we're going from low to medium to high. Very unspecific, intentionally, because these are just examples. Okay, now we're going to have our second axis here, increasing as you go up on that side, is the supply restriction impact. When I'm talking about the impact, I'm talking about the economic impact. How is it going to affect the U.S. economy? Again, low, medium, and high. High impact on the economy, in other words, major economic disruption. Low impact, you won't even know it tomorrow. That kind of scenario. So as we move in that direction, from down here, moving up into that direction on the diagram, that means we're getting more critical for that mineral commodity. That's increasing its mineral criticality. They love that word, so I'm going to use it. Now, let me give you a real simple example here, one that I think can all pretty well agree on. And that's a familiar metal to all of us, gold. The United States, believe it or not, consumed like $15 billion in gold in 2024 alone. Okay, enormous amounts. I forget, it's like 8 million ounces or something of that effect. We are a net exporter of gold. We mine and produce more gold than we actually consume. So that's one of those commodities that gets sold overseas. Part of our exports. And the places that it's mined are considered very safe. Most of it, 70% of this gold, comes from the state to the south, Nevada, which is politically fairly stable. Sometimes I wonder, but it's a good steady supply. 70% comes from there, and something like 20% comes from Alaska, and the rest of it comes from a whole bunch of other states, small amounts from other states. Okay, question?
What about Idaho, and what about the mine they're trying to open over at Stibnite, east of the Cascade area?
Okay, well, that mine is not open, so that mine would not affect anything we're talking about here. All right.
They, put it in the future.
The Idaho mine could factor into that once it gets into production, yes. It will add to that, amount that's produced, for sure. On this diagram, okay, gold would probably sit way up in that corner because economically it's critically important. Why? Because of its impact on the major economies of the world. Okay? All countries in the world hold a certain amount of gold in reserve. They all do. It's gold bars. All right? And then you use gold in other things like jewelry, and there's some that are used in electronics. We use them in commemorative medals, for the Olympics. Well, gold medal, well, that's gold. I mean, we use it in various fashions. But it's importance to the financial end of the economy that really makes it have such a big impact on the economy. So any sort of supply restriction would have a very high impact, but the chances of that are incredibly low. I don't see the state of Nevada, rebelling and seceding out of the United States. Doesn't seem likely. So gold itself would sit there. Okay, does everybody follow sort of the rationale? We're just kind of throwing stuff around here. This is not numerically, sound what I'm doing here, but that never stopped me in the past. Okay, let's take a look at a couple of other metals, okay, that you're probably less familiar with. All right, first one I'll talk about is cobalt. Okay, cobalt's a good metal. Sits here on your diagram, number 27, right smack there in the middle. All right. In 2024, what did we consume? 8,500 metric tons of material, of cobalt. All right, which was worth about $145 million to the economy. Okay. So, it's not as big as gold, but it has a bit of an impact in terms of the size of that consumption. Okay. One of the ringers, though, is that we don't process cobalt in this country. So all the cobalt that we might buy or something like that, or even produce, it all has to be exported either to Canada or China for processing into or refining into the metal that's used. The mines can make cobalt concentrates, but they can't separate out the cobalt from the other materials yet. All right?
I'm curious, do you have any idea in readings or research why we wouldn't decide to process it ourselves?
Well, it probably wasn't processed here. It may have been processed here in the past, but it probably wasn't economically viable to continue to do it. That these other countries can do it cheaper. So it's cheaper to export it, have them refine it, and then ship it back in, and then I can use it. So it all gets down to the economics of the thing. Okay. Our net reliance for cobalt is 76%. So 3/4 of the cobalt we consume, we have to import. Okay. Now we get it from those countries there, Norway, Finland, Japan, and Canada, all pretty good friends of ours. So that's not a great worry. Okay. Now, how do we use cobalt? In gas turbines, some of the super alloys, the metals that we make that can withstand extremely high temperatures. That's important. Rechargeable batteries. It's used extensively in rechargeable batteries. And then various chemical applications. that are too numerous to list up here. The chemical industry uses it in various little capacities throughout all their processing. Not great amounts, but enough that it would affect what's going on. Substitutes, what you get there, yeah, you can't, there are substitutes for this, but you get a loss of product performance in general, or as I mentioned, you get increasing cost. Yeah, you can get the same performance, but it's going to cost you 10 or 20 or 30% more, just because we have to use this other material there. So we've got that kind of information. And there's a bunch of others out there that they use for their evaluation. But just for what we're doing here, one might say, well, cobalt might sit here. Okay, the supply risk potential is certainly not low. There is a certain element of concern there, because if we ship a lot of this to China and they decide that they're no longer going to refine it for us, then that sets up a whole nother set of problems. All right, the economic impact will not be real high, but it will, again, be significant. So one might argue that cobalt is more of a critical mineral than gold is, based on that sort of reason, that sort of rationale. Okay, another example, my second example I'm going to show, bismuth. All right, which sits way down here. Don't realize that bismuth is actually just about as heavy as lead is. One of those elements we just don't think much about. We don't run into it very frequently, and yet we use it. 2024 was at 760 metric tons of bismuth was consumed. Again, these are the 2024 numbers. All right, $9 billion, which economically isn't. It's a drop in the bucket, so to speak. Okay. Net reliance, pretty high, 89%, with 2/3 of that coming from China. And another quarter or so coming from South Korea, and then a smattering of other countries. But the two big players are China and South Korea. China's the one that might be worrisome here if they decide to shut off bismuth. Okay, now, we use it in various curious ways that aren't often appreciated. Okay, it's used in cosmetics.
Oh, yeah.
It's used in pigments to give colors to paints and things of that. It's used in pharmaceuticals. One of the reasons it's used in pharmaceuticals is it's inert.
Is that the Pepto-Bismol?
Yeah, I think that it is used in Pepto-Bismol. Metallurgy, it enhances certain properties to the metals that might be desirable in the conditions that you're looking at. Okay, because it's a lead replacement. It has about the same weight, that it does have the same weight as lead, and yet it doesn't have all the nasty effects of lead. And so you can use it in places where lead would be real handy, but you're worried about contaminating the human body. You can't contaminate the human body with bismuth. It doesn't react. It just passes through. Okay, and also, curiously, because bismuth has a relatively low melting point, it's used as a trigger for fire sprinkler systems. It gets hot enough in the room, the bismuth melts, and that sets off the fire sprinklers. Okay, it used to be they would have a little vial, a glass vial filled with glycerin. And if the room got hot enough, the glycerin would expand, it would bust the glass vial, and that would set off the sprinklers. Trouble is, you're shattering glass, which isn't necessarily, you got a fire going, but that's not necessarily the best way. With bismuth, that eliminates that whole thing. Okay, now there are a lot of common substitutes depending on what you're using it for bismuth. So substitutes are pretty readily available for that bismuth. So bismuth might sit somewhere down here. Supply risk, because of the China connection, again, it's not low. It's probably going to be up in the medium range. But the economic impact, because we've got a lot of substitutes and things like that, okay, is much more restricted. I mean, it's not going to have that big of economic impact. Okay, does everybody sort of get the idea of how we're sort of looking at ranking these things? Okay, good, good. Now, these are the 84, I know you can't read it, so don't squint. It's okay. These are the 84 non-fuel mineral commodities that the USGS tracks and reports on every year. You can find this information about every one of these suckers on their website. They've got extensive information. At the end of the talk, I've got a website that you can go to at the USGS that provided essentially virtually all the information I'm sharing with you today. But it's got everything on it. So how do you look through this and figure out, okay, which of these are critical and which can be considered not critical? And even amongst the ones that are critical, which ones are highly critical, which ones are a moderate level, which ones are kind of a low level critical. That's what you got to do. Okay, well, one easy way to show all that information is on our good old periodic table. Okay, all the colored squares up here are all the elements that are defined as critical elements. There's 50 of them. This was done in their 2022 review. Okay, by law, the USGS has to go through the evaluation process every 3 years to determine critical minerals. Because over even a few years like that, situations can change. Stuff that used to be critical are not critical anymore. Things that were not particularly critical now have become a lot more critical. So they're on a 3-year time frame to review that. And in fact, that's what they're doing this year. Now, speak about that here in just a little bit. Okay, now, the 2022 critical mineral list is also enlarged on the easel in back for your perusing pleasure at the break, which we're coming to here real soon, or after the talk if you want to take a look at it. Again, this is from the U.S. Geological Survey publication site, so it's easily available there. The nice thing is it lists the compounds in alphabetical order, which makes it a lot easier to find stuff. And then it also gives an application list next to it, which is also kind of useful. How is this particular material used in industry? So that's that's what that diagram shows us. Okay, so I'll let you take a look at the big diagram because this one is not really very legible. Now, but I want to go back to this one because I mentioned that every 3 years they do a review. Okay, they have completed their review for the 2025 list and put it out for public comment in August. The public comment period actually just closed at the end of September. So right now, that new list is sitting with the Interior Secretary for his final approval. And if everything, the government opens back up and everything goes on schedule, it's supposed to be published as a final list in November. So we're right in that interval, yeah.
Is the USGS under the Interior Department?
Yep.
Okay.
Yeah. Department of the Interior is where USGS is housed, along with a whole bunch of other organizations. a little while ago, less than a month ago, they actually published a proposed list. So this is what they're proposing. It's not finalized yet, but this is what they're proposing for the 2025 list. And that's what it looks like.
Oh, really?
Okay, so all the red ones we had, okay, are all the same. That was the same one from the 2022. Now, what they're suggesting to add, I've designated in green. So things like silicon and copper and lead, for various reasons, they feel like the situation has changed. And so those metals now should move into the critical mineral stage or designation. Now, you notice I say 54, but they're adding 6. Something wrong with the math? No, nothing wrong with the math. Because what they're also doing is proposing getting rid of 2. Arsenic and tellurium are being off-listed, if you will. They're being kicked off the list.
Well, tellurium sometimes is a waste of product from gold miners, so.
Tellurium, the situation has changed such that we are actually now a net exporter. In 2022, we were not. All right, but in 2020, for the review for 2025, they determined now we are in fact a net exporter. So it's no longer to the level where it's considered critical. And arsenic, as I recall, the import source has changed recently. Used to be China was the big source of our import for arsenic that we use. However, now it's shifted over to South America, Peru in particular, supplies most of the arsenic. And so that puts a little bit greater stability in. Yes?
Can I ask, why is carbon on there?
Carbon, good question. I forgot to mention. There are a couple of placeholders in here, and carbon is one of them. You think about carbon, it's everywhere, right? Why would carbon be? Well,
Because it's diamond?
we're not talking about the element carbon so much as the mineral form of carbon. And Coyote mentioned diamonds, but that's not why it's on here. It's graphite. That's correct. Yes, graphite, which is pure carbon, is a very important lubricant.
Exactly, it's high temperature.
High temperature. That's right. It withstands much higher temperatures than a lot of materials, so the lubricant won't break down as rapidly. So it's important that way. Another one actually over here is barium. The element, we're not so interested in the element barium. What we're interested in, the commodity, is the mineral barite. And barite is used in the oil and gas industry. When you're drilling wells, the muds that you use in the drilling have to be weighted. They have to be heavy to help prevent blowouts down below, high pressure blowouts. And so you weight up the mud with crushed barite. And so the barium is a placeholder for the mineral barite. If you look on the list back there, you'll find barite.
Have we
Yeah.
switched from, well, I mean, I'm surprised letters aren't there, I guess. What's the story for letters?
I do not know. I don't know why it got that they decided to add it to the list. I'm sure there'll be more explanation in the future once this gets finalized. There'll be a justification for that.
Also, barite is very good at stopping radiation. So it's also, that's what lends substitute that.
That's true. Coyote mentioned that barite is useful because it's heavy again for radiation protection. So in nuclear reactors, the cement that goes around the reactor build helps contain the radiation within the vault itself.
Very good insulation.
Okay, so it's break time. Why don't we proceed to get into the second half of this brutality here? And so we will devote the whole time to rare earth elements, because there's a lot of talk about rare earth elements today. So I want to just sort of, again, try to fill in some background on what are rare earth elements. Okay, so to start with, you could look at this diagram. And it's going to be a test. Everyone pick out your favorite rare earth element and circle it. No, that's not what we're going to do. Yeah, all except Coyote, because she's going to circle all of them. If you look on this diagram, actually the rare earth elements are really easy to identify. It's this baby down here, outlined in red. That line right there. All the way across, that whole line are rare earth elements. And I will explain here shortly where that name comes from, because it's not intuitively obvious. In some ways, it's not a very good name, but it's we're kind of stuck with it. And so that's what we're going to call it. Good old rare earth elements. Now, there's a couple other elements which are also frequently included with discussions of rare earth elements. Okay, one of those is yttrium. Element designated by the letter Y. Yttrium is significant because if you know anything about the layout of the periodic table, the rare earth elements occupy a real curious spot. It's like a loop that all fits right in that one square right there. So if you go back, let's go back one, get that number out. It says number 57 to 71. So it does sort of a little time warp in there, and all of those fit right in there. And again, there's a good reason for that, which we'll get into here in a little bit. But yttrium is one of them. Okay, the other one is scandium, which is 21, the one above it. For the purposes of this discussion and the way the U.S. Geological Survey tends to track this thing and group these things, we are going to take yttrium and put it in with this, but we're not going to talk about scandium. And there's one other rare earth element we're not going to talk about. That is number 61 here, promethium, which, if I remember my history correctly, promethium was the last element, naturally occurring element, that was identified and isolated long enough to study it and get the characteristics of it and identified it, filled in a slot. They knew there had to be an element between 60 and 62, but nobody had been able to isolate it. The reason for that is promethium is very radioactive and it's rather unstable. And so they had hints of it. It was like, did I see something there? I don't know. They got a hint of something while doing another experiment, but they could never prove that that's what it was. And it wasn't until the 1940s that some guys at Oak Ridge actually were able to isolate promethium and identify it and give it that funky name, promethium. So the fact that promethium is so squirrely, we're not going to talk about it. So we're just going to eliminate it because nobody uses it. It's not a useful element from our perspective.
I thought we put our money on it.
Yeah, right. Okay. Now, one designation that's given to the rare earths, these 7 rare earths right there are often referred to as the light rare earth elements. Whereas these 7 over here are called the heavy. I mean, real creative here, light and heavy. And the only reason that they use light and heavy is because, like the rest of the periodic table, as one moves from the left to the right along any particular row, you're tending to increase the atomic weight of the element because you're increasing the number of protons in the nucleus, blah, blah, blah. But the point is that these are lighter weight, atomic weight, than this group over here. So they have light and heavy. And another reason that makes a lot of sense from a geologic perspective is that these guys over here tend to occur together. And these guys over here tend to occur together. Sometimes you get mixing between the two, but not a lot of mixing. So they all kind of like to hang out in their own neighborhoods, I suppose. So you may see this, somebody talking about light rare earths. That's what they're talking about, that group.
Well, just like my professor said again and again, minerals are known by the company they keep.
Okay, the company they keep. I suppose that's right. Okay, and we're going to throw yttrium in with the heavies because yttrium, in the way it reacts in the chemical environment and the way we use it, mimics a lot of the properties that the heavies have. And so by convention, yttrium is grouped with the heavies. So we have the light ones and the heavy ones, in case you're run into that at some point. Okay, now, what are rare earth elements? A natural question to ask. Okay, well, this is a group of elements, and they were discovered during the 18th and 19th century, although fully isolated, it didn't happen until the 20th century for some of the particularly tough ones. So they were discovered early on. We knew that they must exist based on how the periodic table was being built and the relationships that come out of that. And so we knew there had to be an element there. So scientists went out and tried looking for this element, trying to isolate it and measure it. Okay, now, at the time, all right, these were earth elements. Because at the time, if you couldn't further change an element, no matter how much heat you gave to it, you couldn't make it any more unstable. It's reached its lowest level. It was basically an oxide at that point, a rare earth oxide. Then it was called an earth. These were earth elements. All right. And the fact that they were less common than the other earth elements they had already specified. Well, what were those elements? Well, those were actually fairly common elements. Things like magnesium and calcium and potassium, sodium. Okay, these were also referred to as earth elements because they couldn't be reduced any further. These were earth, but they were rare earth compared to that. So that's where the name rare earth element comes from, which is really, as you're going to see, pretty much a misnomer. All right? Because first of all, they're not rare compared to other, what we would consider common metals. So I want to run through some stuff here to show you why I can pretty confidently make that statement. So let's back up and look at some of the average crustal abundances. First, we're going to start big picture, okay? And what we're going to have here is the 12 most abundant elements in the Earth's crust. And it's going to have a number associated with it, and that's going to be a percentage. Now, the most abundant by far, the two most abundant, I should say, by far are our good friends oxygen and silicon. Most people don't realize that nearly half of the Earth's crust, half of what you're standing on, is made up of oxygen. Okay, 75 or so percent of the Earth's crust is just silicon and oxygen, two elements. That's why the silicate minerals are so common. Things like quartz and feldspars and all those other things we look at all the time. Just because there's so much of those elements in the crust, that's what minerals get made out of. So that's a bulk of the Earth's crust right there. All right, now, remember, those are in percents. And if you look at the other elements that can be easily measured in percent numbers, there's actually only 6 more. These guys right here: aluminum, iron, calcium, magnesium, sodium, potassium, stuff we've all heard of. Okay, so what we're looking at right here is like 99% of the Earth's crust is made up of those 8 metals. Mineralogy can be very simple sometimes, despite what it feels like. Particularly when you're looking at it on an atomic basis. Okay, but I said 12, so let's round out this. The other 4, titanium, carbon, manganese, and phosphorus, are all occur in the Earth's crust at less than 1%. And so we start getting into decimals here really fast. Okay, down to phosphorus, which is 0.06% of the Earth's crust. All right, well, if we were to get into all the other elements, we're going to get some pretty gnarly looking decimals out there. Too many zeros. So if what you want to do is look at the kinds of stuff we're talking about today, a lot of the metals that we use, the rare earths, all the rest of that stuff, you got to kind of change your thinking a little bit. Okay, so now what we're going to do is we're going to look at the average crustal abundances, but we're going to use a different system. We're going to talk about them in parts per million. Instead of parts per 100, we're going to look at them in parts per million. And for reference, 1% is 10,000 parts per million. So you remember phosphorus before, 0.06? That's the same as 600 parts per million. So the numbers I'm going to be showing you here are all in the ppm, the parts per million designation. I'll let you figure out what it would be in percent. Sharpen your pencils. Okay, first of all, we're going to look at what we would consider the common metals, stuff that we use every day. All right, again, just emphasize, this is in ppm. Okay, a couple common ones: copper, arsenic. Okay, that in parts per million is how they occur in the Earth's crust. If you look at the Earth's crust as a whole, relatively low abundance. Even lower abundance, what's really shocking, is if you look at our precious metals, gold and silver. Actually, to be useful to talk about gold, you typically have to talk in parts per billion, because the numbers get gnarly again if you just restrict yourself to parts per million. They're bulky, so you change over to parts per billion. Fortunately for us, all of these metals have an ability to concentrate through geologic processes, which defines the whole nature of the study of economic geology, is the processes which concentrate these into deposits that we can actually go out and recover the metals from and use. Okay, so those are our common metals. That's just a range of stuff to give you a feel for what that looks like. Because now, let's look at these rare earth elements. And what do they stand at? Surprisingly high values. When you compare it to things like copper and arsenic, it's about the same. There's nothing rare about them babies. Not when you're looking at the total crust, the abundance in the total crust. What's different is that it's the economic deposits. I won't say they're rare, but they're unusual. They're far less common. And so that's what makes them a challenge, and why we only recently really started using them in big ways. That's when the availability of the material matched up with the technology which says, hey, we got a market for this stuff. Sell it to me and I can use it. Technology is what I'm talking about here. Okay, so the technology now has uses for these things. So it's finding these economic deposits has become sort of the challenge. Okay, so why are these rare earth elements, which I'm going to abbreviate as REE, why are they so useful? That gets back to Coyote's favorite subject, which is chemistry. Okay, they're found together in these unusual deposits because they share, first of all, a common ionic charge, which is this +3 charge. They're valence charges. Yeah, they're called valence charges. And they also have a similar size as a single ion, single charged element, which means they can substitute for each other real easy.
Atomic shells,
Yeah, thank you. Atomic shells, similar size. All right, so they can readily substitute. And the mineral that they're substituting into doesn't have to worry about the charge because they're all at this +3 charge, so it doesn't cause any problems to it. So that's one of the reasons that they're so useful. And because of those properties, this allows them to segregate together as a group. But it also means that all the other kids don't want to play with them. And so we don't find them in gold deposits. And we don't find them in copper deposits. But we find them in rare earth deposits. And they're all just happily just waiting for us there. At least that's what I tell myself. Okay. This same charge is what gives them very useful properties from our perspective, because it gives them some somewhat unusual magnetic properties, which we can use and have used, continue to use, and it will give them optical properties, which are unusual and very useful to us. And we'll mention that also as we go along. So that's why rare earth elements are so useful to us. They have certain properties that other elements really don't exhibit. And so they're good, they're useful to us. As mentioned, they're not commonly found in silicate minerals, so they won't jump into your average feldspar, not at any great abundance, or your average quartz, or whatever those other silicate minerals there are out there. They tend to isolate themselves. If they're in a magma, they all kind of isolate themselves, get away from all the other kids. So when they do form a deposit, they're all together. Okay. Next, I want to run through very quickly some of the uses that we have. And rather than going through the elements and saying what it's used for, you can do that with the chart back there. I'm looking at the uses, all right, and some of the stuff that it does, all right. In glass, rare earth elements are used for that really precise polishing that we need. What do we need that for? How about those flat screen TVs that everyone's got in their living room now? You got to have those perfectly polished.
It has to be absolutely clean and black.
So very important. Okay. It's an additive to other glasses for special optical properties that that particular rare earth might impart to it. For instance, some of them absorb ultraviolet lights or wavelengths, which are useful, obviously. Or you can use them, you can add them to glass for glare reduction, like windshields and things of that nature. In some cases, they'll impart a particular color to glass that you can't really get with other elements that might be useful. Europium, for instance, increases the conductivity in optical fibers. Well, that's useful to us, because if we can speed up how fast that information is flowing in that optical fiber, that's better for us. We can do more with it. Okay, yttrium, our good friend yttrium, use that to make special lasers. So the glass that's used to make the laser has yttrium embedded in it to give the emitting light special properties that are useful to whatever capacity the consumer needs. Okay, we use it in catalysts. Now, catalysts are things that we add to speed up reactions. You had a catalyst to steel making, to more rapidly melt things.
Flex agent.
That too. All right. Now, cerium is actually built into automobile catalytic converters because it helps the catalytic converter do its job better. Okay, a lot of us know that there's platinum in a catalytic converter. Yes, platinum is very expensive. Well, there's cerium in there too, because that helps the platinum do its job. Okay, lanthanum, they use that in petroleum refinery. Okay, that's used because that helps break down those really long, large hydrocarbon molecules. Breaks it down better, which makes the processing more efficient. You lose less in the process. Okay, magnets, common thing that we use rare earths for. Okay, permanent magnets are basically all the magnets, the powerful man-made manufactured magnets nowadays are made with the help of rare earth elements, and they have rare earths in them. Okay, one of the strongest known is this neodymium iron boron magnet. Sometimes it's referred to as NdFb, NdFeB, or just the capital letters sometimes, depending on who's reporting on it, how do they abbreviate it. But that's what it means. So it's got neodymium in it, which is the rare earth, and then iron and boron, which are not rare earths, but nonetheless useful elements in there. These are very strong and very useful because they're used in places where space and weight are critical. You're trying to minimize both of those, how much space it takes up and the strength of it. It has to be as strong as possible. Okay, think hard drives, cell phones, okay, both hybrid and electric vehicles, windmills, aircraft, all that kind of stuff. If you've ever looked at an actual hard drive, I mean, you may know what a portable hard drive is, but those have got that plastic case on the outside, so you have to break into it to see this. But a lot of times, this is what they'll have. They'll have something very similar to this mounted on the hard drive. That's the magnet. That's that magnet that's doing some of the work of that hard drive. And these are obviously a couple of examples where weight is a certain consideration, for sure. You can accomplish the same work at less weight. That's greater efficiency. Okay, it's used in batteries. We're already kind of familiar to some degree with their use in batteries. Nickel metal hydride batteries is where they're used. They are basically rechargeable batteries that use alloys of rare earth. Okay, the metal, think rare earth. Okay, primarily it's nickel, but it has other metals in there, including rare earth. Okay, consumer goods use this. If you got, appliances or yard tools or something that have rechargeable batteries, those are the kind of batteries you're probably going to have in there because they're very efficient. They're very good at their job. Okay, usually they'll be marked nickel metal hydride battery. In some cases, they're used some in automobiles, Some electric and some hybrid vehicles use those. Fairly common. However, it looks like in the future, their use is going to be diminished because lithium batteries are making more of an impact, and they're being replaced by these lithium batteries. So it's anticipated that those type of batteries will be left to other specialty uses, and lithium's going to take, particularly in the automobiles, will take over there. Okay, used in metallurgy, as I think we mentioned before. Steel making involves rare earths because of enhancements in it. It helps remove some of the impurities that are in the process that you're trying to remove all the time. Any specialty steels, high strength steels, high corrosion resistant steels, those specialty types of steels usually involve some sort of rare earth involvement. They're used in what are called phosphors. Okay, now phosphors, what is that? Phosphors actually we use all the time. In fact, you're looking at a bunch of phosphors right here while you're looking at that screen. Okay, phosphors are used in cathode ray tubes, fluorescent lamps, flat panels like this, all kinds of stuff. All right, and they're used because what they're doing is that the light that we want to see requires a certain color. And we want to see it. You know, that guy's shirt is red. Well, when I look at it, I want to see a red shirt. All right. Well, how do I make it red on the screen? Well, the electrons on the backside don't know red. They don't know anything. Okay. But the little rare earth elements embedded in this screen, the phosphors, they know red. So you get them excited with some electrons and they emit red light. And so you can see red. Okay, so the color that comes out, whether it's red or blue or green or whatever, is based on the elements in the phosphor. And many of those elements, to get the special colors, particularly the real high definition that we like these days, the amazing colors, the blending of the colors, comes about because of the phosphors in the screen itself. So again, a very useful aspect to it. Now, those are some of the uses. Kind of blew through them fast, but I mean, there's uses in the table back there I've enlarged. You can find it online pretty readily if you're interested in those kinds of things. Because what I want to show you now, what do these little babies cost? What are the prices of rare earth elements? Now, what I'm going to cite here, the prices are in US dollars per kilogram oxide, because that's how it's sold. Okay, so at this point, it's not actually a finished product. It's not just lanthanum. Okay, it is a lanthanum with some sort of stabilizing agent in it. So it's a lanthanum oxide or a lanthanum carbonate. That's how it's sold to the companies that are then going to further refine it and use it in their product. Okay, so these are the sales prices. Now the prices I'm going to show you are from last month on the 16th when I got these. So they're still relatively accurate with one big exception, which I'll mention as we get through there. Now again, to illustrate it, we're going to use this little line of elements from our periodic table because it's just a handy way to do it. Now, don't forget, these are light rare earths, these are heavy rare earths. And the reason I'm putting this up again is because you're going to see a big price difference in general between these two groups. Okay, spoiler alert, them's the cheap ones. Okay, if you look at the light rare earths, these are the numbers in dollars per kilogram oxide on the 16th, according to the Shanghai Mineral Market, which is where this is from. That's what SMM is. So I figured Shanghai, those guys know the prices. Well, I figured they probably do. So it ranges anywhere from lanthanum is just $2 per kilogram, up to what, 79, neodymium. A lot of the price just reflects the difficulty in extracting that from the ore. Okay, compare that with the heavies. Now we're out here in triple digits on some of these. Okay, a lot harder to extract these. Less abundant, harder to get, and so it just drives up the cost more. Through yttrium over here, yttrium is actually fairly cost effective. So that's one of the reasons we use a lot of yttrium in there. Now you can say, okay, well, I can compare it this way, but how does that affect things I'm kind of familiar with in my life? So what I want to do, first of all, is put up some common metals. I realize this isn't oxide, this is the actual metal. You know, it's a pound of copper, or actually it's a kilogram, because I recalculated the price in kilograms, US dollars per kilogram. Copper, $10. For $10, you can get a kilogram of copper if you want it. I don't know why you'd want that, but if you want it, you can get it.
You're making wine.
Okay, I'm making wine. All right, common there. Now, more familiar to us, gold and silver, and it's the gold number that's probably wildly inaccurate. No, not wildly inaccurate. It's about 15% higher than this as of today, or as of Friday anyway, since gold shot up to over $4,000 an ounce. So, and this is per kilogram. Okay. So just to show you, yeah, these things are expensive, but not as expensive as other things. And they're actually in line with other things we've got. Just that how we use them and the difficulty involved in finding them is why they've only recently been used. Now, of the reading I've done in here, it seems like the common ones are the ones I've marked in this kind of pale yellow. So those four, those are the biggies. And then these two, including yttrium. Those six seem to be the most common rare earths that are used kind of in all the industries. There are certain applications, however, where only one of these will work. So that's what you have to go with. Defense contractors, many times, to get the quality that they need for this instrument or this system to work, they need one of these. So they'll pay for it. We pay for it. Okay, that's the government paying for that aspect of it. All right. If you're out selling stuff, if you're manufacturing and selling stuff, then you try to avoid these. Okay, maybe it would work faster if I used one of these, but in reality, that's so expensive that I can keep my cost way down and sell it to you cheaper, and you're only going to see a 3% drop in performance. So it's worth going with the other one, the cheaper one. Okay, now let's look at production of rare earth elements. This is a diagram I lifted from a USGS publication that runs from 1960 on this side over to 2012 over here. And this represents the worldwide mine production of rare earth oxides in thousands of metric tons. So the top number here, can't read it, it's 140,000 metric tons. So in 2012, we were using maybe about 115,000 metric tons of rare earths. That's in 2012, 12 years ago, according, concerning the USGS, data set that we work with. Now, this diagram, the US portion of it is this kind of off purple color, kind of bouncing around down here. So we were producing some at a mine that I will, if time permitting, I'll talk a little bit more about here toward the end. and it bounced around for a while, but we had troubles back in the early 21st century, and it shut down, etc. I'll get into that. Okay. Now, meanwhile, in the 1980s, mid 80s, is when China came on big time with their rare earth production, and it just took off from there. All right. So, what would it look like today, or what would it look like last year when we got that full data set? So, I want to add that to this chart, but I can't do it on here. Okay. So, what we're going to do now is we're going to look at the 2024 total mine production of those rare earth oxides. Again, in metric tons. And I'm going to use that other diagram. Okay, so I'm going to have to put it to scale, so it's going to be way down here, which means that it's even harder to read, but you don't need to read this. Just recognize this line, the top of it is at 140,000 metric tons, and this is at 2012. Timeline stops right there. What we want is what's it look like in 2024. And if you put that up there, that's what it looks like. In 12 years, we're now using 390,000 metric tons. An enormous increase just over 12 years, just over a decade. U.S. share of that is approximately 45,000. The other, which are all the other countries in the world except China, contribute 75,000. And of course, you can still see China produces 2/3 of the rare earths that the world consumes. And that obviously, since we consume a lot of them, our share is even higher than that on a percent basis. So that is a big chunk, a big growth right there. And that's why so many companies are out there looking for rare earths, because all of a sudden the market, which we thought was pretty good here, has just absolutely exploded. Think electric cars. That's one of the big consumers. Yeah, question.
China is not on top of that because they have the resource, but because they have the resource and the refining capacity.
That's part of the story. They also jumped in early in 85. And so the other deposits that are out there in other parts of the world, I'm not ignoring the US for right now, in the other parts of the world, all right, were unable to catch up. And China just took over. And a lot of it has to do with the refining capacity. So they control the production, the mining and processing, and the production of what then they could sell. And they could do it at a scale that undercut all the other companies or all the other countries that are selling things out there on the market, which is one of the techniques that China has always utilized at least in the 20th century. You can see similar things happen with other metals, tungsten being one, where they can flood the market and almost drive other people out of business so that they can dominate the business.
Their restriction or threat of restricting supply is not because the mineral is in short supply.
Correct. Yeah. So it's going from geologic to geopolitical. Yeah, which I'm not here to talk about that aspect of it, but recognize that's boiling in the background. Yes, sir.
What kind of rock types do we find the rare earths?
Actually, I'm going to show you an example of the rock types that we find rare earths in as we go along here. I may run over a little bit, so if you need to leave, feel free to score yourself out. Okay, this is a map, a generalized map, showing where rare earth mines and projects are found worldwide. And it's difficult, you can't read any of the names, and that's okay. That's not what's important. The important thing is they're found all over the planet. They're found all over the place. There's some found in Greenland. The only place we haven't found them, and that's purely because we haven't looked, is Antarctica. But they're basically found all over the place. Now, the big player from the world production standpoint is in China, and it's Bonobo is their big producer. That's the one that's producing so much rare earth that they can maintain control of the market. It gives them the dominance from there. Now let's go from there and zoom in on the US situation. These are rare earth occurrences as of about 2019 of rare earth elements. Kind of scattered around. The red dots show actual locations. In particular, something odd is this kind of yellow zone out here. That yellow zone defines old beach sands.
Yes, that's a silver.
that have black sands associated with them, and within those black sands, they can recover some relatively low grade, but nonetheless not insignificant amounts of rare earths. There's one active mine in the United States that I want to talk about, and that's right here, called Mountain Pass in California. Okay, so I want to finish up with a brief description of the Mountain Pass mine. Now, first of all, where is the Mountain Pass mine? All right, LA sits here, Vegas sits here, Mountain Pass sits literally right next to Interstate 15. So if you've ever driven from LA to Vegas or Vegas to LA, you've driven right past the mine. You could wave to people. I mean, it's that close. It's that close to the freeway, and we're gonna see that here in a bit. So it's out in the Mojave Desert. Okay. Now, to talk about this deposit in particular, first of all, it was discovered in 1949 by a couple of uranium prospectors who went out there and found a slightly radioactive brown mineral that seemed unusually heavy. And so they went and had it analyzed, and it turned out to be a rare earth element containing. And so by 1952, they actually started some mining there because there was small demand at the time for some rare earths. Okay, the ore production lasted until about 1998 when the company shut down due to basically its processing was getting old, it was getting less cost effective, and finally they just decided to hang it up. Okay, it resumed again in 2028, trying to make a go of it, and it lasted till about 2015, and then shut down again. It's had a bumpy ride. It happens, and a lot of it is just because you need to invest a lot of money into it to upgrade the facility to really make it efficient in today's market. Okay. In 2017, MP Materials, which is the current owner and operator of the mine, acquired it, and timing was everything here because the market was exploding and they took it and ran, and they are now our sole producer. Okay, just to throw some more numbers at you here, the proven and probable reserves as of 2024 for the Mountain Pass mine consist of 27 million metric tons of ore. That's ore in the ground. And this is stuff at 6%. Now use this abbreviation. You see this a lot when you get into these things. TREO. That's the total rare earth oxide content. So those 27 million tons, approximately 6% of those is going to be rare earth oxide. Once you mine all of that, process it, and concentrate it. All right. I mentioned this before. In 2024, they produced 45,000 metric tons of concentrates, which had a value of $260 million. Not a bad chunk of change. Of course, that doesn't include what it took to get it out, process it, do everything else, but nonetheless, that's the value assigned to that amount. Okay, now the reserve estimate, if you go through and do the calculations in detail, like they're required to do by the Security and Exchange Commission, because they are a publicly traded, you can find them on the New York Stock Exchange if you're interested. Okay, 1.9 million, approximately 2 million metric tons of total rare earth oxide concentrates. So that's the concentrates. That's not the ore, that's the concentrates. Okay, so that's what's in front of them. That's what they expect to mine over the coming years. Okay, let's a quick look at the ore body. Okay, it is hosted in this really funny igneous rock. Okay, it's called a carbonatite. And it's funny because it is a carbonate-rich, think calcite, carbonate-rich intrusive rock. It's actually rather deficient in things we normally think about intrusive rocks, like silicate minerals. Doesn't have a whole lot. It's mostly, over half of it is carbonates. And in fact, 40% of it is calcite. We don't normally think in terms of intrusive calcite. I mean, calcite, that's limestone. Limestone isn't intrusive. So this is part of the funny chemistry of these babies. Okay, an old cross section, but it works, from 1980 of the mine itself. This represents the potential ore zone at depth. So it kind of dips off in that direction, and it's about 200 to 300 feet wide, or thick, I should say, not wide. And they're mining it from the surface. At the time, that was the proposed depth of the open pit, but that was back in 1980, so it's clearly enlarged from there. They've done exploration drilling, or they did exploration drilling out here, and they can still find this thing 3,000 feet down.
The tectonic.
So it is, I mean, it's deep. It continues at depth. There you're just limited to what can you economically mine from the surface. That's the limiting factor here, not that the ore is giving out at depth. Okay, the rare earth elements themselves is hosted in a carbonate mineral, bastnasite, which most people have never heard of. It's a very rare, actually, mineral, except if you get into rare earth element deposits. And there you see it. Okay, bastnasite, it's a carbonate mineral. It's a rare earth carbonate. Makes up about 12% of the ore. So that block of ore you got there, about 12% of that is this mineral, which then needs to be concentrated and broken down to create the elements, or pull the elements out of it. Okay, that's what it looks like at the surface. I could see if I were walking around and saw something like that, this doesn't look particularly distinctive. Kind of a cruddy brown color laying around. But if you pick it up, it's heavy. It's unusually heavy, which is what the old prospectors keyed in on. It's like, there's something going on here. You know, it's not supposed to be that heavy. Okay, so that's what it looks like on the rock. Okay. Now let's look at the bastnasite in the mine. And this is the average rare earth element distribution within that mineral at the mine. So in other words, these are the rare earths that they're looking at here. And I'm going to use this one. You should be familiar with this layout again. Okay, and if you look at just the mineral that they're recovering, percentage-wise, that's the majority of it right there. Those four rare earths. Okay, lanthanum, cerium, praseodymium, and neodymium. That's like 95% or something like that of the rare earths they're getting out of there. So this deposit is particularly enriched in the light rare earth elements. The others that we find in there are also light rare earths, but at a much lower level. Now that altogether comes up to like 99.8% of the rare earths that you're going to find in the mineral, which means only 0.2% come from this side over here, various sprinklings of those. And make no mistake, I mean, they will recover those. It's just that they're not going to get a whole lot out of them. You know, it's not a big producer of that, but they are going to be getting a lot of that. Okay, this is what the place looks like. I don't know the exact date of this photo. I believe it was about 2023 or something of that nature. You can see Interstate 15 right back here. So wave as you drive by, going over to Vegas. There's the open pit operation. You've got a crusher, which as they take the ore out of the ground, they bring it over here, they crush it, they send it over to a processing plant, which pulls out the bastnasite, concentrates it, does some other processing with it. Then the stuff that comes out of the mill here has to go through a processing, a settling area over here, and then they pump it out to some evaporation ponds. And then the more concentrated stuff from this travels over to this complex over there, where they actually are breaking down the various rare earths, separating them so that they can sell that as a finished product. So really, their limiting capacity here is how much can you get through here for any 1 year. So that's something that they would be working on for sure. That's what the concentrate looks like, which looks an awful lot like those rocks, doesn't it? It's kind of the same color. But they bring it down to powder form, and then that would then get processed. There's your concentrate, and then it would get separated. Take this, separate it out into your cerium oxide and your neodymium oxide, and then over here the lanthanum is as a carbonate. But nonetheless, you separate them out, and some of the other goodies, but those are the big players. That's what they sell most of, and that's where they make that money from that material there. Okay. If you would like to follow up any of this information, I strongly recommend you start by going to the U.S. Geological Survey and visiting the National Minerals Information Center, where they have more than you could ever read. All right, guaranteed, because it takes an incredible workforce to assemble all this information. If you're interested in any mineral commodity, that's a good place to start. And they have annual updates on stuff. For certain commodities, they do monthly updates on production and stuff like that. All kinds of links to other things, just all the diagrams. Most of the diagrams I've used this afternoon all come from this site. They're all available there. So I would encourage you to visit there if you're interested in this. And I'm going to say, are there any questions at this point?
Yes, Jerry.
Okay, what's your question?
I'm asking you about rare earths in this region.
In this region?
Talking about what I've been told when I've been down in Durham, that there is rare earth mining, or at least they are planning for it, about 20 to 40 miles west of Durham, talking about trying to build up an infrastructure so they have to work people down there. I have been to Jackpot and settled down there and talked to a Zach Woods, who's a well-known archaeologist and rock hound down there, a historian, and he says that about 27 miles east of Jackpot, they're talking about doing something like this. And his recommendation is that we get over there, any of us interested in rock hounding in that part of Nevada, and get out everything we can. And we keep hearing about the possibility of an open pit mine in the Boise Basin, similar to the picture you showed.
Was there a question in there?
Yeah, what do you know about all this?
First of all, I have no knowledge of a rare earth occurrence west of McDermott.
I think that's for lithium.
I am aware of a lithium occurrence.
A lithium rare earth.
I don't think they have much rare earths in there. I think it's primarily a lithium deposit.
Critical mineral, rather than
It is a critical mineral, but that's a lithium, and it occurs at the surface, and they are working on evaluating it and designing for an open pit and going through all the permitting that's involved with that.
So
I mean-
something like that is happening, because the area that we're talking about there in McDermott, I've been offered a tour once, and I didn't trust their truck or my car. Something like 20 to 50 feet. Things like this full of opalite.
That would be consistent with where the lithium would be.
You know, and when Zach talks about the area east of Jackpot, he's talking about rocks of that type, minerals of that, gems of that type he finds, including candy opal.
Okay, well, I'm not familiar with opal occurrences in that part of Nevada, so I don't really have any.
Well,
Thing to add to that.
It's the minerals and the semi-precious gems that come out of the rhyolite.
Okay, well, let's focus on rare earths and critical minerals rather than opals.
Okay, there's a problem then. I thought that they were in some ways similar, but we're talking about critical.
Well, critical minerals and rare earths, but rare earths are critical minerals, but there's a whole bunch of other critical minerals too, and lithium is one of those.
Well, what about the Boise Basin?
I'm unfamiliar with any rare earth occurrences in the Boise Basin. I have heard of a copper moly occurrence that might be, they're looking at evaluating anyway. I think they're right now getting permits to do some drilling.
Yeah, okay, it may be that I hear rumors at times.
Well, we all hear rumors.
So essentially, the stuff up in the Boise Basin, we've had rumors scaring us all for 10 years.
Well, actually a good contact for that would be the Forest Service, because whatever's going on there has to get run through the Forest Service, and so they're gonna have that on their website. Are there other questions?
Well, I think let's make the questions sort of individual. Let's all give Terry a big
Oh, thank you.